Bismillahirrahmanirrahim. Assalamu alaikum. We are here to deliver the FIP presentation on hydrothermal carbonization of the municipal solid waste and the coal product as an alternative fuel. I am Ali Ansari with my group Muhammad Anas and Riaz Ali. Here's our agenda: introduction, literature review, problem statements, aims and objective, materials and equipment, experimental procedure, results and discussion, application, conclusions, limitations, future recommendation and references. Let's begin with introduction. Hydrothermal carbonization (HTC) is a thermochemical pre-treatment process that treats the biomass with the temperature from 100 to 240 centigrade temperature under the autogenous pressure to produce the coal-like product is an alternative fuel known as hydrochar. The hydrochar which we get from the HTC reactor is a stable, hydrophobic, brittle product with high caloric value similar to the lignite coal. The hydrochar contains large amounts of the stable carbon and other nutrients essentially used for soil amendment. This picture shows the HTC process. Algae, rice or corn stubbles are used as an input into the HTC reactor. The HTC reactor consists of temperature sensor and pressure sensor, and during the HTC reactor process, the gases are produced in the HTC reactor which are not harmful to the environment. Through the HTC reactor, we get the hydrochar, and the hydrochar consists of the liquid and the solid particles. We separate the solid and liquid particles and we get the dried hydrochar, and that dried hydrochar consists of numerous applications such as solid fuels and soil amendment and etc. HTC deals with the high moisture content biomass and variety of the other waste such as plastic, textile, food waste and other mixtures etc. It treats waste which follow the feedstock to be converted pre-drying. It will help to reduce the waste volume of about 50% and help to reduce the environmental pollution. HTC process has been found to consistently improve the biomass fuel HTC characters by raising the higher heating value HFE of the hydrochar. We reviewed number of the literature and we got that the hydrochar which we get from the HTC process have similar characteristics to the lignite coal. It accepts the waste as well as the mixed biomass. It requires less amount of the energy. It prevents the toxic gas emissions. There are three key parameters in the HTC process: temperature, time and the feedstock. We found that at higher temperature, the lower the solid product is obtained and the carbon content increases while the hydrogen and oxygen content decreases. HTC turns the waste into the valuable carbon. The hydrothermal carbonization takes few hours to convert the waste into the carbon, gas and liquid. Problem statement. According to the Environmental Protection Agency EPA, Pakistan generates around 20 million tons of the waste annually, and this figure grows by 2.4% each year. Pakistan lacks waste management infrastructure like other developing countries such as USA, UK, China, Germany, etc. Having proper waste segregation system, the proper plastic, metal and glass, etc. HTC accepts the variety of the biomasses regardless of the segregation and moisture content. Other technologies have some limitations. They do not convert the mixture of the different types of the biomass collectively into the desired projects. Our aim and objective is to study the effect on various HTC parameters such as temperature, particle size and residence time. Our aim and objective is to study the hydrochar characteristics, qualification degree, HHP, energy efficiency of the hydrochar. Here are our materials and equipment which we use in our HTC project: biomass feedstock, HTC reactor, temperature controller, distilled water, weighing scale, grinding equipment, filtration setup. We started the experimental procedure with the preparation of the biomass. We collected the rice husk, wheat husk and the corn starch to ensure they are free from the impurities. Cleaned the rice husk thoroughly to improve any dust and foreign particles. Grinded the dried rice husk to achieve a desired particle size suitable for the HTC process. Loading of the HTC reactor. Measured and weighed a specific amount of the rice husk, wheat husk and corn starch biomass, about 125 grams, using the weighing scale. Transferred the weight biomass into the HTC reactor. In addition of the water, we added a predetermined amount of the distilled water to the reactor, maintaining a water to the biomass ratio of 3:1. Mix the biomass and water thoroughly to ensure the uniform weighting of the rice, wheat husk and corn starch. In temperature controller, we gradually increase the temperature range from 100 to 180 centigrade temperature by using the temperature control. Maintain the temperature within the desired and thoroughly the experiment. And reaction time, we allow the HTC process to proceed for the specific residence time, typically ranging from 15 minutes to 19 minutes. In filtration and drying, we set up a filtration system to separate the hydrogen from the liquid phase, collected the hydrogen and wash it with the distilled water to remove any residual impurities, transfer the hydrogen to the dry it at the suitable temperature to remove any remaining moisture. Data collection and analysis, we collected the dry hydrogen of the wheat husk, rice husk, corn husk, and pineapple with different residual time. Send the dry biomass to the lab for conducting elemental analysis to access the carbon, hydrogen, nitrogen, sulfur, and oxygen content of the hydrogen. The table shows the parameter effect on the hydrogen from the HTC technology. There were about 3 operating parameters such as temperature, particle size, and residual time. The minimum temperature was 100 centigrade while the maximum was 180 centigrade. The minimum particle size was 0.42 mm while maximum was 0.48 mm. The minimum holding time of the residual time was 15 minutes while the maximum was 90 minutes. There were about 8 responses such as volatile meter, fixed carbon, H content, carbon, hydrogen, sulfur, nitrogen, and oxygen. While using wheat husk at temperature 100 centigrade for the 15-minute time, the volatile matter percentage was 68.8%, fixed carbon was 24.8%, H was 6.4%, carbon was 39.8%, hydrogen was 5.7%, oxygen was 54.1%, nitrogen was 0.7%, while sulfur was 0.48%. We increase the time from 15 minutes to 20 minutes, then carbon ratio increases from 39.8% to 40.53%, while the oxygen decreases from 54.1% to 53.8%. As we increase the temperature from 20 minutes to 20 minutes, the carbon ratio increases by 39.8% to 40.53% and 40.53% to 40.5%. Similarly with the rice husk, when the temperature was about 130 centigrade temperature and the time was 30 minutes, the carbon ratio was about 46.15%. And we increase the time from 30 minutes to 60 minutes, the carbon ratio increases from 46.15% to 48.0%. We compared our data with different studies on the HTC reactor and we found that for wheat husk at temperature 100 centigrade temperature for 15 minutes, the carbon ratio was about 38.7% while oxygen was 55.4%. As we increase the temperature from 100 centigrade temperature to 160 centigrade temperature for 60 minutes, the carbon ratio increases by 98.7% to 47.67%. Similarly with the rice husk at temperature 140 centigrade temperature for 60 minutes, the carbon ratio was about 38.8%. By increasing the temperature from 140 centigrade to 160 centigrade temperature and the time from 60 minutes to 90 minutes, the carbon ratio increased by 38.8% to 49.66%. Similarly with the cone cob, when temperature was about 120 centigrade temperature for 30 minutes, the carbon ratio was about 45.12%. By increasing the temperature and time from 120 centigrade temperature for 30 minutes to 190 centigrade temperature for 60 minutes, the carbon ratio increased by 45.12% to 48.05%. We showed that by increasing the temperature and by increasing the residual time, the carbon ratio was increasing. And results and discussion. The figure 1 showed the biomass feedstock of the wheat husk. Figure 2 shows the hydrogen of the wheat husk, while figure 3 shows the elemental composition of the wheat husk and its hydrogen at different HTC temperature. In this graph, we can see that as the temperature was increasing from 100 centigrade temperature for 20 minutes to 100 centigrade temperature for 30 minutes to 120 centigrade temperature for 20 minutes and so on, the carbon ratio was increasing from 40.05% to 40.07% to 40.1% to 40.15%. We found that by increasing the temperature and residual time, the carbon ratio was increasing. As we increase the temperature from 100 centigrade temperature for 20 minutes to 160 centigrade temperature for 20 minutes, the carbon ratio jumped from 40.05% to 47.67%. The figure 4 showed the biomass feedstock of the rice husk. The figure 5 showed the hydrogen of the rice husk, while figure 6 showed the elemental composition of the rice husk and its hydrogen at different HTC temperature. Here we can see that by increasing the temperature from 120 centigrade temperature to 180 centigrade temperature, the carbon ratio increases from 38.52% to 49.66%. Figure 7 shows the biomass feedstock of the corn star. Figure 8 shows the hydrogen of the corn star, while figure shows that the elemental composition of the raw corn star and its hydrogen at different HTC temperature. Here we can again see that when we increase the temperature from 140 centigrade temperature for 60 minutes to 180 centigrade temperature for 60 minutes, the carbon ratio increases from 46.05% to 49.86%. We found from our experiments that by increasing the temperature from 180 centigrade temperature to 240 centigrade temperature and residual time from 15 minutes to 19 minutes, the carbon was increasing and it was increasing having the similar qualities to the lignite coal. In results and discussion, we can again see that in figure 4, this figure shows the oxygen and carbon ratio and hydrogen and carbon ratio. When we increase the temperature from 120 centigrade temperature to 130 centigrade temperature to 150 centigrade temperature to 180 centigrade temperature, by increasing the temperature from 120 to 180 centigrade temperature, the feed stock we use as our waste to convert into the feed stock is hydrochar. That hydrochar becomes similar to the lignite coal because it has the similar quantity similar to the lignite. Here we can show we can see that in this graph. And similarly for the hydrogen and carbon ratio of the corn stuff, we can see that by increasing the temperature from 140 centigrade temperature to 180 centigrade temperature, the hydrochar which we get from the HTC react having similar quantity to the lignite coal. Applications of the hydrochar. Hydrochar is renewable energy because hydrochar replaces the fossil fuels for the heat and electricity. Hydrochar is biofuel source because hydrochar turns into renewable biofuels like biolin and syngases. Hydrochar can be used for the soil enhancement because hydrochar improves soil, boosting crops and reducing the fertilizers. Hydrochar can be used for the waste management because hydrochar treats the organic waste, reducing its volume effectively. Hydrochar can be used for the greenhouse substrate because hydrochar provides a stable medium for the plant growth. Hydrochar can be used for the green construction because hydrochar strengthens the material like concrete for sustainable buildings. Conclusion. We conclude our FIP project by unlocking biomass potential through transforming the biomass into valuable hydrochar, diversing resource usability. There were about two key factors such as the temperature and the time runway because HTC process holds most hydrochar composition responding to temperature and time variation. Coal-like evolution. Hydrochar which we get from the HTC react aligns with lignite coal attributes as temperature and time isolate. Pakistan waste revolution. HTC emerges as the waste management superhero offering hope for the Pakistan challenges. The limitations which we face in FIP project was high capital cost. The initial investment for the HTC facilities can be substantial, posing challenge for the resource limited country like Pakistan. Water consumption. HTC water demand could be problematic and water scarce areas. Biomass variability. HTC's effectiveness varies with the biomass type, limiting its broad use. Residence time. Balancing production rate and hydrochar quality through optimal residence time is resolved. Waste source variability. Variable waste input leads to unpredictable hydrochar quality and energy content. Future recommendation for the hydrothermal carbonization is financial support. Provide subsidies to offset HTC's high capital cost. Policy initiatives. Offer investment initiatives to promote the sustainable waste management. Localize the HTC unit. Develop small-scale HTC system for decentralized waste to the hydrochar conversion. Public awareness. Educate communities for foster waste segregation and hydrochar utilization. Partnerships. Collaborate with research, industries, and international organizations. And last one recommendation is local innovation. Support the startups and entrepreneurs in HTC technology. This is our project plan. These are the references which we use in our FIP project for the support and help to complete our FIP project.